So I called this problems involving circular motion and other concepts, primarily energy combinations, where there's a change in height, a change in speed, and a circle. Like a roller coaster with a loop. Example 1. A roller coaster barely makes it around, I'm going to underline the word barely makes it around, a vertical loop of radius 4 meters. A says find the minimum height that the roller coaster needs to start from at the top of the hill. And then B says find the normal force, the apparent weight, of a 50-kilogram passenger when the coaster returns to the bottom of the loop. Okay. A wants me to find the minimum height. It wants me to find this. Is there a change in height? Is there a change in speed? This is a job for conservation of energy. That's my first thinking. I'm going to say, okay. Oh, and I guess we're going to talk about this location as initial, and we're going to talk about this location right here as final. Top of the loop. Because it says find the minimum height. We're going to barely make it across. I'm going to start out by saying, okay. Kinetic energy initial plus potential energy initial equals kinetic energy final plus potential energy final. We'll ignore friction in our magic physics world. Are any of these 0? Careful. Look where I've put, where's the final location? At the top of the loop. So no. There is one of these that's 0. Really? I think it's right at rest. This is coming over the top hill. You're almost at rest. Close enough. Let's do that. So I'm going to get a half. Oh, no, not a half, Mr. Dueck. That canceled. I'm going to get mgh initial equals a half mv final squared plus mgh final. Will an empty roller coaster be able to make this loop the loop the same way as a full roller coaster can? Yeah, why? Woohoo! And again, in real life, they don't quite, it's all about if there's extra friction, but we'll grease it down enough that we got a good safety margin. Okay. I guess they want me to find H initial. So I guess I would divide by G. You know what? I'm going to come back to that. Let's look at the right-hand side. H final. You know what? I'm going to tell you that from here to here is the radius. So I'm doing something nice and generic. I know it's 2 meters or whatever. So what's the height at the top in terms of the radius? William? That's kind of nice. So I know the final height, right, Nate? Not 2r. I know G. You know what I don't know? V. Which V? Since you're moving in a circle, it must be the centripetal speed. Must be. So let's draw a free body diagram at the top of the loop. Free body diagram. What are the forces acting on the top of the loop? Get the obvious one. Gravity down. What else? Normal force down. What did I underline? Do you remember? Barely. Now, if we barely make it, if you're barely making it over the top, how heavy will you feel at the top? For a split second, you're going to feel weightless. If I'm barely making it, what I'm really saying at the top is I want that to be 0, the normal force. At the top, the only force that I want is gravity. This is terribly unsafe. This is barely making it. You would shriek in terror because you would feel like you were about to fall off, fall down, however you want to think about it. So, I have this. Gravity equals, what path are we tracing out? At the top of the loop, gravity is what's pulling me around in a circle. Not cosmic gravity this time because I'm on the Earth. Oh, conveniently, M cancels. But what I'd like to do is get the V by itself. How? Get the V by itself. How? Actually, you know what? I just fibbed. I said get the V by itself. But actually, what do I have sitting in my original conservation of energy equation? Not a V, but a V what? So why don't I just be really clever and get the V squared by itself? Huh? Eh? Huh? V squared equals GR. GR. And now, I'm going to put that in there. We get this. GHI equals 0.5 GR plus G 2R. Is that right? And some of you are smiling because something weird's about to happen here. What's canceling now? What? Curtis, what? G, huh? What that means is this. For this roller coaster to make it through the loop, it would work on any planet in the universe. Because the 9.8 unique to the Earth canceled. If you somehow Star Trek beamed this to the moon, it worked just fine. If you somehow Star Trek beamed this to Mars, it would work just fine. The G cancels, which is why I didn't divide by the G earlier. I kind of knew that was going to be coming. So here's what I have. And any of you that someday get into engineering, into ride engineering, I'm sure this is something that every roller coaster designer knows by heart. The minimum safe height to start from, if you want to make it through a circular loop, is equal to 0.5 R plus 2R. Mr. Dueck, those are like terms. Are you serious? Really? What is 0.5 R plus 2R? I love this as being one of the cleanest answers we'll ever get all year. We started out with something, Josh, this complicated. We even brought in a free body diagram. We brought in winner minus loser. We brought in, oh, we're moving in a circle. And we end up, you know what? Turns out, for any roller coaster, if you want to make it through a circular loop, you better start 2.5 times the radius high. Minimum. I don't need a stinking calculator. Put it away, Curtis. 2.5, because what's the radius, Curtis? I think I can go 2.5 times 4 in my head. I think. What is 2.5 times 4 in my head? No calculator required! That's the minimum height. That would be a terrifying ride. Claire, at the top, you would shriek and scream because you would be weightless, which means that you would feel like there was no normal force on you. And as soon as that occurs, we all have the sensation of falling. And our evolutionary heritage kicks in and wants to grab at whatever's, yeah, we don't like that, right? Bigger normal forces we're okay with. We're used to stuff pushing up against us. Smaller normal forces, that's when you really scream. On the elevator, for example, it's far more intimidating when it's going down than when it's going up. When it's going up, you've all felt that stomach feeling before, even going up a hill or something like that. I've felt it before. Not so much when it's going down. So I like that answer. Was that part A or did I divide it into part? Yeah, part A. Let's put a little A there. Okay. You want to build a roller coaster with a circular loop? That first hill better be 2.5 times the height of the loop. In fact, probably you double it or something like that. I'm sure there's a huge safety margin. Now, I've partly fibbed. Hakeem, in real life, it turns out that if you build circular loops, the G-forces on the passengers are extreme. I think I may have told this story, but I'll repeat it. The very, very first circular loop roller coaster was just straight, don't write this down, it was just straight down a hill and did a loop and that was it. It was I think it was at Coney Island. And people would regularly black out. They actually had paramedics and an ambulance stationed at the bottom. You would often get off with nosebleeds. The G-forces are very, very intense for a circular loop. So what we've done in amusement park rides is we have a loop called a catenary. We build the loop in the shape of a teardrop, like that. It's a constantly decreasing radius loop, which is very tough to analyze without calculus, sorry, because the radius is changing all the time. But that lets you approach the loop much slower, and it lets the passengers experience way less G-forces. If you ever go look at a roller coaster loop and try and look at it from the side, I've exaggerated it somewhat, but the more it looks like a teardrop, the tamer the ride is. I've been on one of the, I think I've been on the first roller coaster loop-de-loop. No, at Six Flags Magic Mountain in California, they have the first multiple loop roller coaster. It's already like 30 years old. And there, when you look at the loops from the side, they all look like that. I know in Disneyland, California Screaming does look very circular. I think it's an optical illusion. It's very close. But I know on that one, I feel way more G-forces than, say, on the casual, where it's obviously a teardrop-shaped loop. It's called a clothoid. Did I say catenary? It's called a clothoid loop. It's called a... Okay. So I got to be full disclosure here. You have never been on a roller coaster that has a perfectly circular loop, because you haven't got whiplash and nosebleeds and blacked out. B. Find the normal force when the coaster returns to the bottom. Okay, at the bottom, there we go. What are the forces acting on them at the bottom? Get the obvious one. What else? Normal force pointing which way? Why did I draw the normal force so much bigger than gravity? What path are we tracing out? A circle. So where must my net winner force be pointing? Toward the... So I know that I better draw normal bigger. In fact, it's going to be this. Normal minus mg equals mv squared over r. The normal force is going to be mv squared over r plus mg. Do I know g? Check. Oh, math doesn't cancel this time because it doesn't have the normal force. Do I know r? 4. Do I know v? Oh, v. Hey, look at the picture. Is there a change in height? Is there a change in speed? Is it a curvy, yucky path? Any suggestions for how I could find the velocity at the bottom? Is there a change in height? Is there a change in speed? Is there a curvy path? Any suggestions for how I could find the velocity at the bottom? Conservation of energy, you say? Hey, let's do that kind of off over here. We could say this. Kinetic initial, potential initial equals kinetic final plus potential final. N8 initial kinetic is 0. This time, however, we can also say we're at the bottom. I'll get mgh initial, which I guess is 10, because we just figured it out in part A, equals a half mv final squared. Yay! Oh, you know what? V final squared is 2gh initial. Let's go plug that in over here. Normal force equals m 2gh initial over r plus mg. This person's going to feel heavier at the bottom because normally you feel mg, and we've also got m2ghi over r added to that. They'll feel heavier at the bottom. Let's see, the normal force is going to be, what did I say the mass was? 50? Okay. 50 times 2 times 9.8. We just figured out my minimum safe initial height is 10. What was the radius, Curtis? 4 plus 50 times 9.8. How big is the normal force? You get 2,940 as compared to 409. This person's going to feel really heavy at the bottom. Like I said, if you do a circular loop, the g-forces are pretty intense. How intense at the bottom? And this is minimum safe speed, by the way. 2,940 divided by 490. They're feeling 6 Gs right now. That's minimum safe speed. So, what did I say? 2,940 newtons. So, fun theory, not so much fun fact. Although, this is assuming you're right on the track. This is assuming your head's on the track, essentially. And in real life, that's not so much the case. Your head and your center of mass are removed about a meter or so from the track. We could probably take that into account, and we might get some different results. We may actually be able to pull off a loop. Put your pencils down. Okay, back to physics. At the top of the 12 centimeter, give me a second here. I'm debating which ones of these I want to do. I think, in the interest of time, although this is really a nerdily cool question, I'm going to temporarily nuke that one. Example 2. A satellite in orbit around the Earth is at radius r and speed v. The satellite is hit by a small rock and slows down somewhat. And let's use our imagination to say it slows down exactly in the same direction as its orbit. In other words, the rock doesn't knock it towards the planet or away from the planet. By a wonderful coincidence, it gets hit straight on with the rock, so it loses kinetic energy, and that's it. Yeah, I know we're in our magic physics world again, Jordan. You with me so far? What happens to the radius of its orbit? The final orbit has radius as before. The final orbit has a bigger radius. The final orbit has a smaller radius. And it says explain your answer using principles of physics. Okay, let's try and do a proof. Did I say orbit? I did. If we're in orbit, what might you be tempted to approach this with? What might you want to write down as your first approach? Let's do it right up here next to the diagram. Gravity is what's pulling me in a circle. Gravity is always big G, big M, little m over r squared. Circular motion is, circular force is m times circular acceleration. Which circular acceleration do I want to use? The one with the period or the one with the speed in it? Yeah. Now what? If I was trying to make a prediction, if I was trying to do a proof, now what? What do you think I want to get by itself? Cliff? The R. I went to go see a pirate movie the other day, but I couldn't get in because it was rated R. No? Okay. The R. No, I think what I want to see, because I'm talking about radius, I want to get the R by itself and then see where the velocity appears in the expression so that I can say, well, if the velocity gets smaller, which is, apparently it is, what happens to the radius, right? Let's see, get the R by, you know what? I think I'd probably multiply this up here. You know what? I think we get this. R equals big G, big M over V squared. No square root necessary this time, I don't think. No? I heard someone make a comment. It was Peter or Nate. What'd you say? Looks like because the V is on the bottom, as we slow down, what we're really saying is the further the satellite is away, the smaller kinetic energy it needs, the slower it can travel. Of course, the more potential energy, the more fuel you had to burn to get it there, so you can't win. It's a trade-off. But final orbit has, I think, a radius, what'd you say? Bigger. Explain your answer. Oh, you know what? We should actually make our conclusion. I've done the proof, and then I should simply say, as V decreases, R increases, and there's my proof. I did the proof, but I didn't get the conclusion. Don't want to do that. Technical comment. This orbit would probably actually be an ellipse that passes through the collision point and then moves closer to the Earth on the far side of the orbit. We're treating all of our orbits as nice circles because that's what we got to deal with right now. Like many other things, Peter, what I've taught you this year, this unit, is technically wrong, but close, close. Example 3, is this the last one, I think? Yes, it is. Finish off with this. A 965 kilogram satellite in orbit around a planet has a gravitational potential energy of that much. Its orbital radius is that much, except it's not 8.85 times 106. It's to the m power. It's 8.85 times 10 to the 6th, and assume that the m power is supposed to be meters. Sorry, apparently I wasn't careful with my subscripting, right? All right. A. What's the mass of the planet? How could I figure that out? By the way, there's another typo. Wow, I'm noticing. That should be negative because we're relative to 0 at infinity. How can I figure out the mass of the planet? Apparently I can't. Oh. Well, I thought about that, but the problem there, well, let's try it. Don't write this down. I don't think that's going to get us there. Don't write this down. My first thought would be this, which would be big G, big M, little m over r squared, which is going to be m. Did they tell me the speed? No. Did they tell me the period? You know what? I'm going to have an unknown here and an unknown there. I'm going to have two unknowns. Good thought. I'm going to end up in a dead end. I think I'm going to do this later. In fact, I think to do part B, I'm going to find the speed, but I think part A, I've got to find the size of the planet. Well, what else have they given me, Nathan? What else have they given me? Well, let's see. That's potential energy is negative big G, big M, little m over R. That's got a big M in it. That's got the mass of the planet. Do I know everything else in that equation? They gave me the potential energy in the question. I know little m. G is always 6.67. You know what? And they gave me the radius. Hey, I can find the mass of the planet. I think the mass of the planet is going to be R PE over big G, big M, no, not big, big G, not big M, big G, little m. And there's going to be a negative, although I'm also going to put in a negative for the potential energy. The negatives are going to cancel. Yeah? It's going to be 8.85, Mr. Dueck, times 10 to the 6th. Negative 6.55 times 10 to the 10th, all over 6.67 times 10 to the negative 11, 965. I'm just going to ignore the negatives. Oh, because there was a negative in front too, sorry. Just ignore the negatives because they're going to cancel. 8.85 times 10 to the 6th times 6.55 times 10 to the 10th divided by bracket 6.67 times 10 to the negative 11 times 965. Ha! I bet you they started out with like 9.00. I'll go 9.006 just to be really safe. Times 10 to the 24th. Oh. It's about twice as heavy as Earth. Not quite. So there's my final answer to 2 or 3 sig figs, but I'll keep a few extra sig figs because I have a feeling I'm going to use this later. B. All right, Nate, what do they want me to find in part B? Now we're in orbit. Yeah. Change colors, Mr. D. Gravity equals centripetal. I can tell you guys are getting tired. Can I jump straight to the punchline? I think V was equal to the square root of big G, big M over R. Right? I apologize for doing that minutia, but I can see you guys. I've been talking a fair bit, and I want to show you a couple more cool videos as well. It's going to be the square root of 6.67 times 10 to the negative 11, 9.006 times 10 to the 24th, divided by, what was the orbital radius? 8.85 times 10 to the 6th. Square root of that. That seems about right. Our speeds have often been in the thousands or tens of thousands. 8,240 meters per second. Is that okay, Harjote? Good. Then. Harjote, what does C want me to find? How would I find the kinetic energy? How do I find the kinetic energy of anything since physics 11? It hasn't changed. Yep. I hope you said squared at the end of that, because I think I've drawn some pictures on some of your tests occasionally. Yes? You went a half mv squared. You didn't go a half mv squared, right? Sorry, what's the kinetic energy equation, Harjote? Oh, that's it, girl. Half mv squared. Okay. Did they give us the mass? Yeah? Did we just figure out v? You know what? In the interest of time, because you guys are getting kind of dozy, good enough. Claire, what does part D want me to find? Oh, what does the word total mean? Add them up. You know what? Total energy is going to be the answer from part C plus negative 6.55 times 10, plus the potential energy. It's kinetic plus potential. Yeah?
This one's also the negative kinetic energy, right?
No, no. It should be, the total should be the same as the kinetic but positive in theory if I've made up numbers that are legitimate. So the weakness might be I might have made up this radius and this energy. So let's find out if I did. A half m. What was the mass? V squared times 2. Please give me 6.55 times 10 to the... I did. Whew. I was a little worried that maybe I'd made numbers up. But you are correct. As a shortcut, we could have taken that potential, assuming Mr. Dueck did the math correctly ahead of time, and said, oh, divide by 2. That's the kinetic. Ditch the negative. Oh, and the total, it's the kinetic, but negative. Yes. What's your homework? Take home quiz. I think you can try number 1, number 2. Four, 5. No, you guys have done a lot of orbit. I think you're good on that. 8. Sorry, I skipped 3. So far I've done 1, 2, 4, 8. So far I seem to be going up by powers of 2. 2 to the 0, 2 to the 1, 2 squared, 2 cubed. Ooh, no, 10's overkill. That's got a collision. But which I guess would mean momentum, and I could find the velocity that I need after the collision, and then work my way back and figure out the velocity I need before the initial, and then that would tell me what the height had to be. I mean, that's kind of cool, but that's overkill. Asteroid... Should I do 16 just to keep with my powers of 2? Meh. You know what? I think just those ones alone are good practice for today's lesson. Your other homework is the take-home quiz, and you can now start working away on the big review. Your test is a week from today, Monday. I'll be doing a tutorial Thursday after school. I'll email tutorials out.